Welcome, students. Okay, so in today's session, so we are going to look into the Bayesian learning. So already we have discussed why this Bayesian learning is very important. So Bayesian learning, now it provides a probabilistic approach to inference, right? So now what do you mean by inference? Already we have seen. So you are going to infer something from the data or the knowledge what you are having, and this, by using this Bayesian probability or Bayesian reasoning, so we are going to put some probability approach. So when we have got so many set of hypotheses, say you have some hypothesis, say that tomorrow, based on the weather forecasting report, so tomorrow what is the percentage of rain, right? So or based on certain data, now you try to use projection, like say in today's news they were already telling that in Bangalore, so today around 30,000 plus cases will come. So now you are going to infer something, you are saying 30,000 based on the probability. That means it is telling us that the chances. So when you are talking about the probability, now what do you mean by probability? The occurrence of an event, the likelihood of occurrence of an event, we call it as a probability, right? So when you toss a coin, when you toss a coin, so what is the likelihood of occurrence? What is the probability of occurrence that you are going to get head? What is the probability of occurrence that you are going to get tail when you are going to toss a coin or roll a dice, right? So now that what we call probability and inference. So based on that probability, now you try to infer. So you have got some hypothesis H1, H2 or some statements you are trying to make, right? So now you are going to say that okay, the probability of occurrence of when you are going to roll a dice, so the probability of occurrence of a number 4 is 40%. When you roll a dice, the probability of occurrence of 6 is 60%. The probability of occurrence of 1 is 80%. So we try to fix, then you try to infer. So when you try to infer that, now when you are going to roll a dice 10 times, so based on that particular statement what you have made and what the likelihood of occurrence, then you can try to make a particular statement which is saying that this particular hypothesis I can select, or you are going to infer something. So that is what we call it as a the probability and inference. Now hypothesis, already we stated that what do you mean by hypothesis? Generally you are going to make one particular statement, so that we call it as an hypothesis. So we are going to define a hypothesis. That means you are going to make a general statement, right? So by looking into the lot of researchers or the scientists, they made one, let us say that they made one general statement that in this entire world around 10% or around 20% of the cancer patient recover in a lifetime, right? That is one general hypothesis. Based on certain studies, they make a statement, they make a general statement, or they make one hypothesis that if any particular patient or a person gets a cancer, then what is the chances that he can recover from that disease, right? 20% or 0.2. So that is one statement, or what we call hypothesis. Now that is one general hypothesis. Then based on some data, we are going to collect the data. Based on that we can take some other, we can try to infer something. That is how we call it as a hypothesis. You are going to make one particular general statement, right? So now we have seen. Now say for example, now I just make one particular statement, and generally we call it as a null hypothesis. So I will say that I have a statement H0. Now what is this null hypothesis? So I am going to say that we try to make one statement that 20% of the people who gets the cancer, so they recover from that particular disease, right? And I make another, or let us say that the null hypothesis, I make that say for example, if you are taking the current pandemic situation, so if you study all the pandemic diseases, right? So there was some of the various in this entire world. So past we had lot of pandemic diseases we were having, like say chicken pox, flu, some type of swine flus, etc. Now studying all those pandemic, they make one particular hypothesis saying that so 80% of the or people, or 90% of the people, they recover from that particular pandemic disease, right? So now I can make another contradiction to that when I say that 80%, so that means I can say that 80% does not recover. Or say, for example, another simple example, now as let us say that next month there is one competition which is going to held. There is a game. Now I want to send my students to participate in that game. Now I make a general hypothesis saying that, so that maximum number of students is going to fail in that particular hypothesis. I make one null hypothesis, so maximum students will fail. And I make another hypothesis, alternative hypothesis H1, so which I make that maximum number of students are going to pass that particular examination. Now these are the two hypotheses I am going to make. So now I have got certain time. Now in that time I will be collecting some data. I will train you in such a way that I have to reject this hypothesis, because the hypothesis telling maximum students are going to fail. But I don't want my students to fail in the examination, right? So now based on that data, now I can either reject the hypothesis or I can accept the hypothesis. So this is how we can say define a hypothesis. Similarly, we have got pre-error probability. Pre-error means, so already now before you collect the data, before you are starting your experiment, now you have got some set of old data, or what we call pre-error probability. You already calculated. Now generally pre-error probability you are going to get from an expert people or a domain knowledge whoever is having. So you have some set of probability for this thing. That is what we call pre-error probabilities. So now these are the very important terms. So now which is very helpful for us to understand. So what is called as the Bayesian learning or Bayesian reasoning when you go. So now this is a very important concept, or what we say which can be applied in our machine learning. So now if you look into the introduction, now it is based on the assumption that the quantity of our interest, now whatever the examples we are going to take, our particular interest, it is governed by probability distribution. Now you will be having a probability distribution of all your samples. We are going to associate some numerical values. So then only we try to say that, okay, the probability of this hypothesis is this much, the probability of this hypothesis is this much, right? So it is important for our machine learning programs or the algorithm learning, because it provides a quantitative approach. So it is going to give a quantitative approach for us to weight or to see that whether that hypothesis, you can accept that hypothesis or you can reject that hypothesis, so that it supports various set of all hypotheses when you are having. So Bayesian reasoning, it provides the base for learning algorithms, so that directly manipulates the probabilities. So when you have got 2 or 3 algorithms in front of you, then you can apply the Bayesian learning and say that what is the chances, which algorithm is doing better for me, right? Those things we can try to understand by using this particular Bayesian learning. So now here, so now this learning method, now it is relevant to our study of machine learning. So why? Because there are 2 ways why we try to apply the Bayesian learning. So one is the Bayesian learning algorithm. It calculates explicitly probabilities for hypothesis. As we already stated that here you can explicitly identify or calculate the hypothesis. Now when you are making a statement that, so making a statement that 90% of patients who get the pandemic disease recover from that, only 10% may not recover, they may have the side effect or they may die. So you are telling that 80% of the patients are recovering from any pandemic diseases. So 80%, how do you got that? By applying the probability, right? So wherever the learning algorithms where we calculate explicitly probabilities for hypothesis, then it is a very good for us. And also they provides a useful perspective for understanding many machine learning algorithm. So even machine learning algorithm which do not explicitly deal with probability, now for those algorithms also, now we can try to apply the Bayesian learning, right? So now this is Now there are some of the features. Now features of Bayesian learning method. Now these features, again, it's a very important question with respect to the examination. What are the important features? Now if you look into the first one, now each observed training example can incrementally decrease or increase the estimated probability that a hypothesis is correct. Now you made one particular hypothesis, right? So now today I made a hypothesis that in the next month in the competition maximum number of my students are going to fail in that competition. Now I have to reject that hypothesis. I want my student to pass. Now how I can have the data? I need a data which will support that hypothesis, which is going to say that yes, that hypothesis what I made is correct. So I can get only with the data. Right, I give everyday training for that competition, I conduct the exercises, I give certain assignments, I take the test day by day, slowly at the end of the month, based on all this data, now I can make either accept or reject the hypothesis. So after 1 month of rigorous training to my students, now what has happened is that hypothesis which I made that the students are going to fail in the examination or in the competition, it can be rejected because I have solid proof with me. These are increasing. That is what we say, every observed training data, it either increases if I am giving proper training to my students and if they are doing all the exercises correctly. So then what happens to that probability of failing? So it initially the maximum number of students are going to fail. That was my hypothesis. Suppose out of 10 students I am sending for a competition, I make a statement that 9 will fail. But 1 month when I give a training, every day the training and you also keep on learning, that 9 students who are going to fail, so that might come to 1 student. That means 9 is going to pass the examination. So my hypothesis has decreased, the estimated probability of that hypothesis decreases. So I can reject that hypothesis. So based on the observed training data. So that's what it said, that each observed training data, either it increases my estimated probability whether that hypothesis is correct or whether the hypothesis is wrong. So it can either increase or decrease, but you can only judge based on the training example. So this is one feature. So this provides a more flexible approach to the learning algorithm that completely eliminates a hypothesis if it is found to be inconsistent with any single example. So already we have seen candidate algorithm, finders algorithm, ID3 algorithm. Now there and all, when you have set of hypotheses, how we are going to reject a hypothesis, how we say that this particular hypothesis is inconsistent with a set of all training example. If one example is not able to satisfy, then we are telling that okay, this hypothesis is rejected because one example it is inconsistent, but it might be consistent with many other examples. So that is the reason why here we say that Bayesian learning method, it provides more flexible approach for us. So because we try to consider every training examples and which either increases or estimates the probability of our hypothesis. So this is one feature. The second feature is pre-error knowledge can be combined. Now already we told that we consult before you start an experiment, now you will be having some knowledge about that. We are going to collect some pre-error knowledge, pre-error probability by consulting an expert or a domain expert in that particular field. Now that pre-error knowledge, it can be combined with our observed data. Right? Now you have got a pre-error knowledge saying that 80% of the patient who got pandemic disease, they recover from that. Now, right now in this situation, we got one pandemic disease, that is COVID. Now every day you are observing some data. So yesterday what was the data? How many patient was recovered? Or last week how many patient recovered? This week how many patient recovered? So like this every day. So what you are doing now, you are going to combine that previous knowledge, whatever you are having, that is the pandemic diseases, whatever you are having in that particular knowledge. With that particular knowledge, now you are going to add that. So the what data you got right now, you add it to the old knowledge and you can try to make the inference. You can try to infer right? So my prior knowledge was telling that 80% is going to recover. It might be any pandemic disease. That is what the prior knowledge I have. Now for this pandemic disease COVID, based on the data samples what you are going to collect, you can add that also to that, and you can try to infer something. So what is the another important feature is the previous prior knowledge can be combined with the observed data to determine the final probability of our hypothesis. So to determine the final probability of the hypothesis. So in Bayesian learning, a prior knowledge is provided by a prior probability of each candidate hypothesis. How do you get that prior knowledge? By applying probabilities to each and every candidate hypothesis. So every hypothesis you try to apply the probability. That means you are going to look the frequency of occurrence, the occurrence of that particular event. So you are going to look into the occurrence of that particular event of that particular probability. So with that you can try to collect the prior knowledge. And the second way is a probability distribution. So when you have got an observed data, we can draw a probability distributions of that observed data for each possible hypothesis. So how many are going to pass this particular examination? About then, how do you calculate that how many will pass in the external examination? Now based on the previous results, based on the internal marks, now all that I can have a probability distribution. So with this, so we can try to calculate the prior probability or prior knowledge. The third important feature is that Bayesian methods can accommodate hypotheses that make probabilistic prediction. So whenever you can apply the concept of probability and you can predict something. So there the Bayesian method is very helpful. It can accommodate, it can take all such type of hypothesis where you can have some predictions, where you can apply the concept of probability. Clear? So the next feature is that new instances can be classified by combining the predictions of multiple hypotheses weighted by their probability. So new instance, so when a new example comes, now you can classify this particular example by combining the probabilities of multiple hypotheses. See, every hypothesis when you are going to take from our hypothesis set, now you will be having some probability, right? Now when a new instance comes, say for example, now you got one particular one new instance, say you want to classify a ball. Now you have three classifications. So ball of category A, category B, category C. Now you have a new instance. Now to which class you have to put this ball? Whether you have to put it in category A, or you have to put it in category B, or you have to put it in category 3. Now there what you do is, so we can combine the predictions of multiple hypotheses. So you will be having that probability. So the probability of this ball to go into class A is, like say, it gives us the 80% the chances based on certain features I am telling. Because based on certain features only you are going to classify that ball into three categories, A, B or C. So we can classify the new instance by combining the predictions of multiple hypotheses. Now these hypotheses are given some weights by their probability. Based on that you can try to classify. Even in cases where the Bayesian methods proves computationally interactable. So now we have certain, see, when we are saying applying the Bayesian concept, you are talking about probabilities. When you take a very complicated example, so calculating probabilities of each and every hypothesis takes lot of time, lot of computation power is involved for us. Even though you are going to have lot of computational powers, but still the Bayesian methods, now it provides a standard for taking an optimal decision. So with compared to the other practical methods, even though we say lot of calculations are required here, so when you are doing calculations lot of time is required, but still the Bayesian methods, it proves to be a better way in which you can try to make a decisions for lot of practical examples. So So next, now what are the practical difficulties? Those are some of the features of our Bayesian methods, or applying the Bayesian methods in our learning program. So one practical, what we can say, practical difficulties what we are going to get when applying this Bayesian method. So this particular, the first important difficulties what we are going to face here is that one Bayesian method is that when you are going to apply this particular Bayesian method, they typically require some initial knowledge of many probabilities. So when you are going to apply, so later we will see. So we are going to look into the what is called as the Bayesian rule. So let me. Okay. So when we look into the Bayesian rule, you will come to know that to apply that particular Bayesian rule or Bayesian method, we require some initial knowledge of many probabilities. We should have what are that probabilities, what are the notations, will be shortly we will be seeing. So, but one practical, that's what, so if it's not so easy for us, we need to calculate so many probabilities, so many prior knowledge is required for us, some initial knowledge of many probabilities is required for us before we jump into the actual conclusion. So when these probabilities are not known, when we are saying that we need to have some prior knowledge, some prior probability we should have, right? When this knowledge is not known in advance, they are often estimated based on the background knowledge. Every time we can't say that we will be having the knowledge. So in some cases, in certain experiment, we may not be having the prior knowledge. Now at that time, so it can be estimated based on the background knowledge or previously available data or assumptions. So we can even assume something for our underlying distribution. So that can also, that is one very what we can say practical difficulties. If you don't have, if you have prior knowledge of the distribution, then it's well and good, we can straight away go and apply. But if you don't have, what to do? Right, that is a question for us. So how to tackle some of this pandemic diseases? If you don't have any knowledge how you were tackling some of the pandemic diseases, so that is very difficult for us. Now you can see that. So this particular COVID, so the past pandemic diseases, whatever we got in this world, it was limited to one area. So we had certain type of a pandemic disease which was only in Western countries or in certain regions. But this is the first pandemic. COVID is the first pandemic disease which has acquired or which had shown its effect in entire globe or entire world. Very few places are there where you have not seen disease, but majority, every countries have got this particular disease. It's the first pandemic disease, right? So as I am saying that, so if you don't have that particular prior knowledge, so then it is very difficult for us. That is a practical difficulty what we can find when you are going to apply the Bayesian network. The second one is that the significant computational cost. As we told that when you want to have the various initial probabilities, you have to calculate. Lot of calculations are required. When you do the calculations, lot of computations is required for us. That is another practical difficulties. But we can remove this second practical difficulties because, as you people know, that nowadays we have got very sophisticated machines are available, very fast machines are available. So through which you can somehow manage with the computational powers. But still, we say that is another practical difficulties what we are going to face. So these are the two important practical difficulties. So with this, now we come to the very important concept of this particular module, that is fourth module, that is Bayesian theorem. How we are going to apply this particular learning? So based on this very important theorem called as the Bayesian theorem. It was given, it is named after that particular researcher Bayes. So you can later on do a research about this particular researcher, right? So now when we are talking about this Bayesian theorem, before we are going to state the Bayesian theorem, so let us look into some introduction of why it is very required. Now in machine learning, now we are often interested in determining the best hypothesis. right? So we want to have the which is the best hypothesis. So we have some set of hypothesis space. Already from past 3 modules we are discussing what is hypothesis space, and right. So we are having so many hypothesis space. Now when you consider this hypothesis space H, now what is our interest is that we want to determine what is our best hypothesis. Now what is our best hypothesis? Now we want to determine that. So best hypothesis from some space, hypothesis space, given the observed training data D. Now this is very, very important for us. How you can tell that one particular, suppose say that for example you take an hypothesis H1 from this set of all hypotheses. Now how you can say that, so you have got this one is the best hypothesis. So when you have got H1, H2, H3 like this, if you take 3 hypothesis set, how you are going to tell which is the best? We want the best hypothesis only, right? So now if one hypothesis is saying that there is 90% chances that tomorrow rain is going to come, another hypothesis say that 80% chances that rain will come, another hypothesis is telling that so 50% chances tomorrow is rain is going to come. So which one you want? You want the best hypothesis, right? So our example, like you say, during election time, right now in the next month we have some elections in some 3 to 4 states. Now each, when they give a exit poll surveys, so they will be giving that, okay, based on one particular company, there might be so many company A, I can call company A hypothesis 1. Now they, according to that particular data analyst company, what they are doing, what survey they have conducted, and they came to a conclusion. They say that a party A is going to get a majority votes with so many seats. Another company is going to tell that so party B is going to get, the third one is going to say that there will be an equal tie in the elections. Now which one I have to take? Right? So in machine learning, we are often interested in determining the best hypothesis given the observed training data set. So now if your data set is different, based on some of the training data set, you make one hypothesis. Now whether that hypothesis you are going to accept or not, it depends on the training. If this training data set, if I am not training properly, my students cannot pass the examination, right? They cannot pass that game, they cannot pass that competition. To make them pass, to make them win that competition, I should give this proper training, or the students has to learn properly, right? So the observed training data is very important. Given the observed training data, based on the observed training data, you should select the best hypothesis from the given set of all hypotheses. Right? Now one way to specify what we mean by the best hypothesis is to say that we demand the most probable hypothesis. How? So now you tell, okay, you want to select the best hypothesis, sir. You told that best hypothesis has to be selected. How? How you are going to select the best hypothesis? Right? It's very simple. It depends on the most probable hypothesis given the data D, given the data set sample D, plus any initial knowledge about the prior probability of various hypotheses. So now if you have got a particular hypothesis H1 which says that, right, so which says that, so if you calculate the probability, which says that so 0.2% the students can win the competition. Another hypothesis is says that 0.5 can win the competition, right? So now on what basis? So now you are going to tell which one is good for me, which is the best. I can select this H2 because 50% chances are there, right? So one specific way is that we are going to demand the most probable hypothesis. So you are going to tell this particular hypothesis is most probable. If out of all the hypotheses, one hypothesis is telling that there is a chances of rain, tomorrow rain will come, 90% chances are there, I can take that. So how you got that? Given the some data to prove that that hypothesis is correct. If you want to accept that particular hypothesis, I need some data. Without data, I cannot simply blindly say that, right? Given the data D, given the training example D, which based on this, now you are going to say that one instance, when a new instance you are going to take, that new instance should be consistent with that particular hypothesis. So that can be done by having some initial knowledge about the prior probability of various hypotheses. So you should have some initial knowledge of the prior probabilities, right? Now this Bayes theorem, right, Bayes theorem, now it provides a way to calculate following things. What this Bayes theorem is going to give us. So first one is probability of a hypothesis based on its prior probability, right? So now what it says, that the Bayes theorem provides a way to calculate probability of a hypothesis based on its prior probability. That means if you are going to apply the Bayes theorem, we should have this knowledge about prior probability. Now you should have the knowledge about the prior probability. So you are going to consult some of the domain experts with that particular domain expert. Now you are going to have some prior probability. So when you will see that shortly, we are going to see what are the equation for the Bayesian theorem. Now this Bayesian theorem, when you are going to apply, one of the important thing what we need is, we need the prior probability. Without that we cannot do anything. The second thing is that the probability of observing various data given the hypothesis. So the probability of observing various data given the hypothesis. So we are going to say like this: the probability of observing the data. Now you try to observe some data given this particular hypothesis. Already hypothesis you have stated. For this particular hypothesis, now you try to look the observed data and calculate the probability of this data with respect to this given hypothesis, right? This is another thing. Then the next one is observed data itself. You are going to calculate the probability of the given data. So these are the three important, we can see the components of our Bayesian theorem. Now let us look into some of the notations what we are going to use, or terminologies what we are going to use in our Bayesian theorem. So this is very, very important. You have to understand this very carefully. So the first one we call it as P of H. P means what? Probability. Small h. Small h is what? Hypothesis. Capital H is the set of all hypotheses. Now you have set of all hypotheses. That is a big set is there. In that you are taking one hypothesis, small h. Probability of that particular hypothesis H. So this P of H, what we call, this is nothing but the initial probability. So P of H is what? It is the initial probability that the hypothesis H holds before we have observed the training example, which is generally called as the prior probability. So we were telling from quite period of time, or before we started this particular concept, we need some prior probability, right? We need some assumptions, or we need some data which we are going to collect from domain expert before we start anything, before we start experiment, before we start observing the training data. We need to have some prior probability. So this is called as P of H. Sir, what happens if that data is not there? If we don't have such prior probability, then we might simply assign the same prior probability to each candidate hypothesis. So we can apply the same prior probability. Now what is the same prior probability, right? So say for example, you don't know, when I roll a dice, we don't know what is the probability of getting 6, right? Can we tell that? Can I tell that if you roll a dice, out of from any 6 numbers are there, out of this anyone have to get? Until and unless you are a Shakuni. If Shakuni is rolling a dice, whatever the number I tell, the same number will come. So 100%. But when you roll a dice, I don't know what is the probability. So I don't know the prior knowledge. You are not a Shakuni, right? You are a normal human being. So I don't have any knowledge that when you roll a dice, you are going to get 6 or 4 or 1. I don't know. So now what I do, I assign equal probabilities. That means when you are going to roll a dice, you are going to get the sample space. What will be the sample space? From 1 to 6. Any one number of 1 to 6 you are going to get. So if you roll a dice, now what is the chances that 1 you are going to get? Number 1 you are going to get 1 by 6. When you roll a dice, what is the probability that you might be getting 2? It is 2 by 6. Now 1 by 6, 2 by 6, see what we see is that now we try to assign the equal probabilities. Now what is this? What is the probability? Sorry, what is the probability that you are going to get 2 when you roll a dice? Again it is 1 by 6 only. So we try to assign equal probabilities as we don't know priorly, right? So if prior knowledge is not there, then we simply assign the same prior probability to every candidate hypothesis. So this is what P of H. P of H is what? Prior probability of the given hypothesis. Next, P of D. What is this capital D? Capital D is set of all sample space. Sorry, set of all sample data set what you are going to have. Now P of D, what you call, this is the prior probability that the training data set D will be observed. You are going to calculate the probability of your training data set, so which you are going to call it as P of D. This is the second parameter, and the third one is P of D given H. How we are going to rate this? So we are going to rate probability of D is what? The data set, given data set. Probability of this given data set given that slash, don't write it as divided by symbol, it is slash, given that for this hypothesis H. For this particular given hypothesis H, you are going to calculate the probability. So probability of this data training data set D given the hypothesis H, probability of observing this data D given some world in which hypothesis H holds, given a particular hypothesis. Now this particular hypothesis holds good in our set of all hypotheses. For given this hypothesis, you are going to calculate the probability of our observed training data set, which is called as probability of D given a hypothesis H. The next term is probability of hypothesis H given the training data set. The probability that now this H holds, probability that hypothesis H holds given the observed training data. Now this we call it as posterior probability of H. So we are going to call this as the posterior probability of the hypothesis. Now you can understand that what is required for me to calculate. I want this posterior probability. You are saying one hypothesis, right? So now I have to prove, I have to see that whether this particular hypothesis is being convergent, consistent, whether I want to accept the hypothesis or whether I want to reject the hypothesis. On what basis? Based on this observed training data D, based on this D, right? Probability of this hypothesis which holds good based on the given training data set, which is called as posterior probability. Now I want to calculate this. These are some of the important terms which we have to understand. With understanding these important terms, now we are going to look into what is called as a Bayesian theorem. Now what it provides? Now it provides a way to calculate the posterior probability. As we told, what we want to calculate, probability of this hypothesis, given hypothesis, whether this hypothesis is consistent, it is converging, right? So whether you can accept this hypothesis or whether you are going to reject this particular hypothesis. So when you say that when you are going to have some data based on the given data set D, right? So if you get a probability that one person is telling the chances of probability that tomorrow is going to rain is 20%. Now are you going to accept this or not? Now you are having a general prior knowledge saying that in the month of, let us say, October, 90% chances that rain is going to come, right? So that is a general statement you are having. Now this hypothesis, can you accept? or can you reject? So that is what we call posterior probability. So the Bayesian theorem, what we are doing with this Bayesian theorem, we are going to calculate the posterior probability P of H given D from the prior probability P of H. How are you going to calculate this? The equation. How do we calculate probability of H given this data set D is equal to probability of D given H. The probability of this data set D given H multiplied with the P of H. What is this P of H? Probability of this particular hypothesis. So this we call it as a posterior hypothesis. Already we have seen, right? So it is called as posterior hypothesis. So probability of D given H into probability of H divided by probability of your data P of D. So this is the equation. This is a very important equation of our what is said the Bayesian theorem. Now if you look into this particular equations and if you have understood the terms, individual terms, what is posterior probability, what is the probability of a given data set given the hypothesis and probability of data set, now we can try to draw some conclusions here. The probability of this, that is LHS, posterior probability, increases when this term increases. This is a normal mathematics, right? So this posterior term, the left hand side will increase with your prior probability P of H and with P of D given H according to Bayesian theorem. If the numerator is increases, then obviously this posterior probability increases, and this term will decrease as P of D increases. Your probability, this posterior probability will decrease if your denominator increases. That is how the calculations is going to work. So as the data set, again it depends what type of data set you are going to collect. The more and more data set you are going to collect, then we see that the more probable that the D will be observed independent of H. So now what happens, later we will see when we go. So we try to, because when we are looking here the probability of only the D, nowhere it is linked with the hypothesis. Now we try to ignore this. So later we will see, right? Now this is what the Bayesian theorem says that. So it is used to calculate the posterior probability, that is probability of hypothesis H holds good given the training example D is equal to probability of D given H multiplied with the prior probability of H divided by probability of the given data set, a training example. This is what the Bayesian theorem says. So next we are going to look into another important term which is called as the maximum a posterior hypothesis. So, or it's also short form, it is called as MAP, maximum a posterior hypothesis. What is the meaning of this? Now in many learning scenarios, the learner considers some set of candidate hypothesis, right? We have some set of hypothesis. You are going to consider some set of hypothesis when you are going to do the learning, and is interested in finding the most probable hypothesis out of all the hypotheses in the sample or the set of all hypothesis set. Now he wants to find most probable hypothesis given the observed data set. For a given the data set, observing that data set, out of these so many hypotheses, which one is most probable? Which is that most probable hypothesis? Right? So now when you say that you have got on hypothesis H1, you have an hypothesis H2, you have an hypothesis H3. So now when you calculate, now it is telling this is 0.2, now this is telling 0.4, and the another hypothesis is 0.5. 0.2 means 20%, right? So the hypothesis is 20%, 40%, 50%. Now out of this, which is the maximum? Which is the best one? Which I can consider, right? So now it depends upon the observed data. So now that learner wants to do it. The learner always, out of set of all hypotheses, now learner considers, so when the learner considers some set of candidate hypotheses, he is interested in finding the most probable hypothesis. So any such maximally probable hypothesis. Now out of this, which one is maximum? Out of H1, H2, H3, H3 is maximum 50%, right? So now such probable hypothesis, maximum probable hypothesis, is called as maximum a posterior hypothesis. We are going to call this as a maximum a posterior hypothesis. I think it is clear now. You out of this, now as a learner, I want to learn, I want to consider maximum posterior hypothesis. So now how we are going to look, or how we are going to come up with an equation for this, that is a maximum a posterior hypothesis. Now we can determine the maximum a posterior hypothesis by using Bayesian theorem. Now we try to apply that Bayesian theorem to calculate the posterior probability of each candidate hypothesis. So H of MAP, so maximum a posterior hypothesis, is equal to argument max, arg max. Arg max means what? So out of H1, H2, H3, you are going to find which is maximum, right? It is just like saying one function you are putting, one function. So arg max inside bracket 0.2 is there for H1 hypothesis, 0.4 is there for H2 hypothesis, 0.5 is there for H3 hypothesis in our previous example. Now you have a maximum function. What this function will do out of these three numbers, it will give you 0.5. It is just like that, right? So arg max of H, small h belonging to capital H, of P of H given D. What is this P? That is the posterior probability. So you calculated this. How you are going to calculate this? Probability of this hypothesis given observing this training data set. What is this equation? This is your LHS of your Bayes theorem. If you look into our Bayes theorem equation, this is your left hand side, right? It is nothing but our Bayes theorem. So by using this Bayes theorem, we calculate the posterior probability. Since this is our Bayes theorem, now we replace this. What is probability of H given D? It is equal to probability of D given H into probability of H divided by probability of D. We substitute this Bayesian theorem here. Now this can be written as probability of D given H into probability of H. Now what is the difference between this and this line? Denominator. We have ignored this denominator. So why we have ignored this? Why you have left that denominator? It is very simple. This is probability of a given data, observed data, but nowhere it is associated with any hypothesis. But what is here? What you are going to actually want? You want maximum. You want a maximum posterior hypothesis related to hypothesis. So whereas this P of D, nowhere it is associated with any hypothesis, I can treat it as a constant. So I can neglect that constant and I can remove this denominator and I can say that now H MAP. Now what is this H MAP? Is equal to arg max of H belonging to capital H, probability of D given H, right? Given one particular, for a given hypothesis, so probability of your data set, probability of training data set D multiplied with prior probability P of H. So this gives us what is called as the maximum a posterior hypothesis, right? Now in some cases, now we assume that every hypothesis in H is equally probable, right? In some cases, as we told, when you are rolling a dice, probability of getting 1 is 1 by 6, probability of getting 2 is, again it's also same, probability of getting 3 is also same, right? In certain cases, we might be having an equal prior probability because we don't have the prior knowledge. In that time, what we told, when you don't have this prior knowledge, prior probability, we will assign equal probability to all. So in that case, what happens? Probability of Hi will be equal to probability of Hj. If you have 4 hypotheses, probability of all the hypotheses H1, H2, H3, H4 will be the same because we don't know the prior probability. Now for all Hi and Hj in our set of all hypotheses. Now we can further, in that case, when you say, we can further simplify this particular equation as follows. Right? In this case, the below equation can be simplified and needs only the term P of D given H. Because now this probability of H, what we told, pre-error probability, now this for all the hypothesis is same. That means again it is a constant, right? So now what we can do, we can ignore this also. We can ignore this particular term. When you ignore this particular term, so then we simplify this as argmax of H belonging to the set of all hypothesis H, probability of D given the hypothesis H. Now this we call it as ML, right? So this we are going to call it as maximum likelihood hypothesis. Now what is this maximum likelihood hypothesis? See, till here we were having H of MAP, maximum a posterior hypothesis. Now we have simplified this. In some cases when you have pre-error hypothesis, P of H is pre-error hypothesis. In some cases when you don't have the pre-error hypothesis, you don't have the pre-error knowledge, then what we are going to do, for all the hypotheses belonging to the hypothesis set, we assume equal probability. When you assume equal probability, then that becomes a constant. We can ignore that particular term. Then I can call, now we can call this HMAP, H maximum a posterior hypothesis, as HML. So that is maximum likelihood hypothesis. Now it is called as a maximum likelihood hypothesis. So probability of D given for a hypothesis H is often called the likelihood of that particular data given H. So what is the likelihood of that particular data for a given data set? So what is the chances that that particular data set holds good for a given hypothesis? That maximizes. So again we are telling maximizes, right? So we have argmax, we have a function which gives the maximum. That is why we call it as maximum likelihood hypothesis. Clear? So P of D given H is often called the likelihood of data D given H, and any hypothesis that maximizes this P of D, any hypothesis you have a maximum argmax function, any hypothesis that maximizes this P of D given H is called as maximum likelihood hypothesis. So we define this as HML. Clear? So don't get confused here. HMAP is the maximum a posterior hypothesis, and we have calculated, we have derived an equation. We came to how to find the maximum a posterior hypothesis by using Bayesian theorem, and we have seen that when you are going to apply the Bayesian theorem, we got a situation where we were having two terms, probability of D given H into probability of H, and we assumed in some cases when you don't have the pre-error knowledge, at that time we can remove that, we can think that as a constant, because all are having same probability irrespective of hypothesis. Right here we are saying for all H belonging to H, you might be having 4 hypotheses, H1, H2, H3, H4, or you might be having many hypotheses. For all hypotheses, probability are same or equal. So then we can treat it as a constant, right? It doesn't matter for us. So you are going to remove. Then if you remove that, then we call it as maximum likelihood hypothesis. Clear? So now you try to understand these concepts carefully. So in the next class we will take an example and we will see that, or in the next section, so we'll take one particular example and we'll see how we are going to use the Bayesian theorem, right? So how we try to apply all these concepts. So we'll be trying to look those things in our next sections. So with this we'll try to close this topic here itself. So you try to learn properly, try to look into this video properly, because they should not you should understand these concepts, because it's very difficult initially to understand the concepts. So I just try to listen carefully, try to look into the textbooks, try to understand, so that in the next classes we'll take a simple example and we'll try to see how we can try to apply all those things. Clear? So we'll wind up the session. here itself. Thank you very much.